There's a number that cybersecurity experts, government intelligence agencies, and the world's most powerful financial institutions are quietly staring at right now, and that number is changing everything. Not gradually, not theoretically. Right now in 2026, with published research sitting in peer-reviewed journals and on the desks of officials at the NSA, the number of qubits required to break the encryption protecting your bank account, your Bitcoin wallet, your medical records, and the secure communications of every government on Earth has just been slashed. Dramatically. Suddenly. With the help of artificial intelligence. And the researcher at the center of it looked directly into a camera and said, "The world is currently, in my view, not prepared." This is not a clickbait story. This is not speculation dressed up as science. Every number, every name, every claim in what follows comes from published research, peer-reviewed papers, official government responses, and direct quotes from the scientists who did the work. What Google's quantum AI team and a startup called Oratomic, founded by former Google researchers, have just demonstrated is one of the most consequential scientific developments of this decade. And most people have no idea it happened. To understand why what just happened is so alarming, you first need to understand the system that is now under threat. And that system is the mathematical foundation of almost everything secure in the modern digital world. Every time you visit a website with a padlock in the address bar, every time you tap your phone to make a contactless payment, every time you send a message through an encrypted app, every time a government transmits classified information, every time a hospital transfers a patient record, the security of that transaction rests on a branch of mathematics called public key cryptography. Specifically, on the fact that certain mathematical problems are computationally easy to perform in one direction, but virtually impossible to reverse. The most widely used of these is elliptic curve cryptography, a system in which two parties can establish a shared secret over a completely public channel, using the mathematics of points on an elliptic curve without ever transmitting the secret itself. The security of the system does not depend on keeping the method secret. It depends on the fact that reversing the calculation, working backwards from the public key to the private key, requires a number of computational steps so astronomically large that even the fastest classical supercomputer on Earth, running continuously for the entire age of the universe, could not complete it. That is the lock. And for decades, it has held. Classical computers, no matter how powerful, cannot break it within any practical time frame. The mathematics is simply too hard to reverse. The lock is secure. Quantum computers change the equation entirely. In 1994, a mathematician at Bell Labs named Peter Shor published an algorithm, now called Shor's algorithm, that demonstrated how a sufficiently powerful quantum computer could factor large numbers and solve discrete logarithm problems exponentially faster than any classical method. Exponentially faster means not 10 times, not 100 times, not 1,000,000 times, but faster by a factor that grows without limit as the problem gets larger. A classical computer attacking elliptic curve encryption gets proportionally weaker as the key size grows. A quantum computer running Shor's algorithm does not. The mathematics of the attack scales in a way that, above a certain threshold of quantum computing power, breaks the lock completely, not partially, completely, in minutes or hours rather than billions of years. The question that has haunted cryptographers and government security agencies ever since Shor published his algorithm in 1994 is simple. When will a quantum computer be powerful enough to run Shor's algorithm at the scale needed to break real-world encryption? That question is the difference between a theoretical concern and a civilizational emergency. And for decades, the answer has been reassuringly distant. Estimates published before 2025 consistently suggested that breaking the SEC PT256K1 elliptic curve encryption used in Bitcoin, one of the most widely deployed standards, would require a quantum computer with somewhere between 4 million and 10 million physical qubits. 10 million qubits. The most advanced quantum processors in existence in 2025 had a few hundred to a few thousand qubits. 10 million felt safely distant, decades away, at the pace of hardware development. Time enough to prepare, to migrate, to build new defenses. Those estimates have just been shattered. On March 30th, 2026, 2 research papers were published simultaneously and independently that changed the global security conversation overnight. The first came directly from Google's quantum AI team. The second came from Oratomic, a startup co-founded by Dolev Bluvstein, a researcher who had previously worked at Google Quantum AI before departing in early 2026, alongside others from Caltech and UC Berkeley to form the company. Both papers attacked the same target. Both used optimized implementations of Shor's algorithm. And both arrived at conclusions that security experts described as shocking. Not because quantum attacks on encryption were unexpected, but because the resource requirements had dropped so far, so fast, that the timeline everyone had been planning around was no longer valid. Google's paper calculated that breaking the SEC2's OIM6K1 elliptic curve encryption protecting Bitcoin transactions would require a quantum computer with approximately 500,000 physical qubits. 500,000. That is a reduction of between 8 and 20 times from previous estimates of 4 to 10 million. The full technical details of the optimized algorithm were withheld in the published paper. For explicit security reasons, the team disclosed the result, but not the complete methodology. But the result itself was verified using a zero-knowledge proof, a mathematical technique that allows the correctness of a conclusion to be independently confirmed without revealing the underlying method. The verification is real. The result is real. But the Google paper, alarming as it is, was not the one that made security experts reach for their phones. The Atomic paper was. Because what Blovstein and his co-authors calculated, using a different quantum hardware architecture, specifically neutral atom quantum computers with reconfigurable qubit arrays, was something that researchers described using a word you almost never see in peer-reviewed scientific literature. They described the resource requirement as shockingly low. The Atomic paper estimated that breaking P256 elliptic curve cryptography, not just Bitcoin's standard, but the standard protecting a vast range of internet security protocols worldwide, including HTTPS connections, digital signatures, and secure government communications, would require just 10,000 reconfigurable neutral atom qubits. 10,000. Not 10 million. Not 500,000. 10,000. To understand why that number matters so much, you need to understand where quantum hardware actually is right now. Companies are not building 10,000 qubit neutral atom machines in the distant future. They are building them now, or are within striking distance of doing so on current development roadmaps. PsiQuantum, which became the world's most funded quantum startup in September 2025, after raising $1 billion, is pursuing million-qubit photonic processors. IonQ, using trapped ion technology closely related to neutral atom approaches, demonstrated a 12% speed advantage over classical supercomputers in a real-world simulation in March 2025. Microsoft's Majorana 1 chip, introduced in February 2025, is based on topological qubits with a claimed path to 1 million qubits on a single chip. The hardware is advancing on multiple fronts simultaneously across multiple competing architectures. And the Atomic paper says that one of those architectures, neutral atom quantum computing, could threaten the encryption protecting the global internet at a scale of just 10,000 qubits. And here's the detail that has intelligence agencies and cybersecurity officials most unsettled of all. Both papers confirm openly and explicitly that artificial intelligence was instrumental in finding the algorithmic improvements that produced these results. Blovstein told Time magazine directly, and this is a direct quote, "There is no question that we used AI to accelerate this development." The researcher who had been working on the quantum algorithms told a contact at Google's quantum initiative that he had been using AI and seeing lots of crazy results. Shortly after those conversations, in late March 2026, Google posted a job listing for a quantum researcher specifically to develop AI-based discovery pipelines, automated systems for using AI to find new quantum algorithms at speed. The feedback loop is already being formalized. AI finds better quantum algorithms. Better quantum algorithms reduce the qubit threshold needed to break encryption. Lower qubit thresholds make the threat arrive sooner. And the AI searching for those algorithms is getting better every month. Scott Aronson, one of the most respected independent voices in quantum computing research, a professor at the University of Texas at Austin and operator of the widely followed blog Shtetl Optimized, reviewed the papers and described their combined effect as fundamentally changing the Q-Day calculus. Q-Day is the term used in the cryptography and national security community for the moment, when a quantum computer becomes powerful enough to break widely deployed encryption in practice. For years, Q-Day was a distant theoretical horizon. After March 30th, 2026, it became a near-term engineering problem. The United States National Institute of Standards and Technology, NIST, had previously set a 2035 deadline for critical systems to complete migration to post-quantum cryptographic standards. Multiple quantum computing experts who spoke to Time magazine after the papers were published agreed that the results from Google and Atomic could significantly shorten the development timeline for a dangerous quantum computer. The 2035 deadline, already being questioned before these papers, is now viewed by many in the field as dangerously optimistic. The NSA and NIST are the U.S. government agencies that would typically have input on the publication of sensitive research of this kind. Blovstein declined to specify which government agencies his team had consulted before publication. What he did say was that the Atomic team thought carefully about which parts of their methodology were responsible to publish, given the potential consequences. The paper draft does not mention the use of AI in deriving its key results. But Bluestein has confirmed that a follow-up paper detailing the AI methodology is being prepared for publication. What does this mean in practical terms? For ordinary people, the answer right now is nothing immediate. The quantum computers capable of exploiting these algorithms do not yet exist. The threat is real, but it is not instant. There is still time, perhaps a few years, perhaps a decade, to migrate to post-quantum cryptographic standards before a hostile actor, whether a nation-state or a criminal organization, builds a machine powerful enough to exploit these findings. But Bas Westerbaan, a cryptography researcher who reviewed the implications for time, put the stakes in language that is difficult to dismiss. Almost every system in the world, he said, becomes vulnerable altogether to a quantum attacker once the hardware threshold is crossed. Not weakened, not partially compromised. Vulnerable altogether. Data leaks, extortion, businesses and government systems taken offline. The entire architecture of trust that underpins the digital economy, the padlock in your browser, the PIN on your payment card, the secure channel carrying your private messages, built on mathematics that a sufficiently powerful quantum computer can dissolve in minutes. The post-quantum cryptographic standards do exist. NIST finalized its first 3 post-quantum encryption standards in August 2024, based on mathematical problems, primarily lattice-based cryptography, that are believed to resist quantum attacks. The algorithms are called Kristall's Kyber for key encapsulation, and Kristall's Dilithium and Sphinx Plus for digital signatures. These are real, standardized, implementable solutions. The tools to protect against the quantum threat are available. Google has already internally set a 2029 target for migrating its own systems to post-quantum standards, ahead of NIST's official 2030 guideline. Cloudflare, which provides internet security infrastructure for millions of websites globally, has been deploying post-quantum cryptography in its systems since 2022 and has accelerated that rollout following the March 2026 papers. The problem is not the existence of solutions. The problem is the gap between having solutions and having deployed them across the entire global digital infrastructure. Banks, hospitals, telecommunications companies, power grids, government agencies, military communication systems, all of them run on encryption built around classical cryptographic assumptions. Migrating all of that to post-quantum standards is not a software update. It is one of the most complex and expensive infrastructure transitions in the history of computing. It requires identifying every system that uses vulnerable encryption, replacing the cryptographic libraries, updating hardware where necessary, reissuing certificates, and testing everything under real-world conditions. For large organizations, this process takes years. For governments and critical national infrastructure, it can take a decade or more. And the Oratomic paper just told the world that a decade may be exactly the margin that remains. But to understand where this threat comes from and why it arrived so suddenly, you need to go back one step further, to the machine that made all of this possible, to the Willow chip. Google's Willow quantum processor is a 105-qubit superconducting chip that represents the current frontier of quantum hardware. The numbers printed on its specification sheet are almost difficult to believe. Across its entire 105-qubit array, Willow achieves single-qubit gate fidelities of 99.97%, entangling gate fidelities of 99.88%, readout fidelities of 99.5%, all operating at speeds measured in tens to hundreds of nanoseconds. These are not theoretical maximums. These are measured, confirmed operating parameters on a real chip running in real experimental conditions. In October 2025, Google demonstrated the Quantum Echoes algorithm on Willow, the first ever verifiable quantum advantage over classical computers for a real-world scientific application. Not a synthetic benchmark, a genuine physics computation, completed in seconds, where the world's fastest classical supercomputers would have needed days. A 13,000 times performance advantage, confirmed and verified. Over the course of that project, the Willow chip performed 1 trillion individual quantum measurements, a number that represents, as Google itself described it, a significant portion of all measurements ever performed on all quantum computers combined. Since its introduction, Willow's performance has continued to improve through post-release engineering refinements without changing the chip itself. This is the hardware on which the encryption attack calculations are based. And this is the hardware. The 3 Nobel Prize winners, John Clark, Michel Devoret, and John Martinis, who received the 2025 Nobel Prize in Physics for the foundational research that made superconducting qubits possible, spent 40 years building the theoretical and experimental foundation to make real. In early 2026, Google proved something that the entire quantum computing field had been working toward for a generation. By increasing the number of physical qubits in a surface code, the dominant quantum error correction architecture, Google demonstrated that error rates actually decrease as the system scales up. This is the threshold. the moment when quantum computers stop being fragile, error-prone experimental devices and start behaving like reliable computational machines. This is the point that theorists had predicted for decades as the gateway to truly fault-tolerant quantum computing. IBM reached a complementary milestone in May 2026, successfully interconnecting 4 Flamingo quantum processors to create a 4,000-qubit modular system that operates as a single logical unit. The hardware race is no longer theoretical. It is an engineering sprint funded by hundreds of billions of dollars across Google, IBM, Microsoft, IonQ, PsiQuantum, and a dozen other companies, all converging on the same threshold from different architectural directions. And woven through all of it, accelerating every aspect of algorithmic development, is artificial intelligence, not the narrow AI of voice assistants and image generators. AI systems specifically designed to search the space of possible quantum algorithms, to find the mathematical shortcuts that human researchers, working through problems manually, would take years or decades to discover. Google has now formally begun building these AI-based discovery pipelines. The Oratomic team used them and found results Bluestein described as crazy. The feedback loop: AI finds better quantum algorithms, better algorithms reduce hardware requirements, lower hardware requirements bring the threat closer, is not a future possibility. It is a present reality, operating right now, publishing results in peer-reviewed journals, being read by the NSA and NIST and the cybersecurity teams of every major bank and government on Earth. Here's the summary of where the world stands as of June 2026. The encryption protecting the global internet was designed on the assumption that reversing certain mathematical operations is computationally impossible. Quantum computers can reverse those operations, given enough qubits and a sufficiently efficient algorithm. The qubit threshold required to do so has just been reduced by a factor of up to 20 through AI-assisted algorithmic optimization, from estimates of 10 million qubits to 500,000 for Google's result, and to just 10,000 for Oratomic's neutral atom architecture. Quantum hardware is advancing rapidly on multiple fronts, with multiple companies on roadmaps that approach or exceed these thresholds within this decade. Post-quantum cryptographic standards exist and are available to deploy. The window to complete the migration of global digital infrastructure to those standards is narrowing faster than almost anyone outside the specialist community realized before March 30th, 2026. Bluestein said it plainly. People in the know will say, "It is coming. The world is not prepared." He is right, and the question now is not whether the threat is real. That question has been answered. The question is whether the institutions that protect the world's digital infrastructure will move fast enough to answer it in time.